So we've started to work on finding partial derivatives, but one thing that we haven't really looked at yet is implicit differentiation in partial derivatives. So let's say we have the following function. We have x squared plus y squared e plus z squared equals 1. And if you remember from your intro to 3D and 3D planes, right, this is going to give you sort of a sphere, a unit sphere, of course, of radius 1, just centered at the origin. And so what if you wanted to ask a few questions about how z is changing with respect to x and y? So this would be namely partial z, partial x, or partial z, partial y, or what if we went even eccentric and we said, how is x changing with respect to y? So the answer to all of these questions can be found with implicit differentiation. And this is something you almost absolutely heard about in your Calc 1 class. And so today we're just going to extend that to functions of multiple variables. And you'll see it's actually decently similar. There's not a whole lot more to it. So let's look at this example in particular. If you remember from Calc 1, what we did is we would take the derivative with respect to the variable we wanted of this entire function. So we'll do the same thing. We'll take the partial. Remember this is an operator. When we write it without any value up here, that means it's acting on something. So we'll give it something to act on, which is this entire equation. So we'll take the derivative or the partial derivative with respect to x. And in this case, we want to find partial z, partial x. That's what we'll start with. So we're taking the derivative, partial derivative of everything with respect to x. And when we do this, one thing we can remember from partial differentiation is that we can essentially treat y as a constant. And you may think, like, why can we treat y as a constant? Well, it's actually a very similar reason to why we were able to treat y as a constant in the past. It's because we're trying to see how z is changing when x changes. But we don't care about y changing. In fact, we don't want y to change. So we'll just say it's a constant. And when we say it's a constant, everything works out for our math. And that's the correct way to do it. So we'll go term by term. The derivative of x squared with respect to x is 2x. Remember, y is a constant, so derivative of y squared is going to be 0, or partial derivative, I should say. And this one, z is dependent on x, because that's what we're trying to find. So we want z to be changing, so we'll have to take the derivative of it, and that'll be 2z, and we'll use the chain rule. So then we'll have to multiply by the derivative or the partial derivative of z, and that's partial z, partial x. And derivative of a constant is always 0. And so already right there, we have exactly what we want to find, partial z, partial x. And so we can solve for partial z, partial x. And this yields us negative 2x over 2z. I'm going to skip a few algebra steps, and that's negative x over z. So I think that's pretty cool. And it was pretty simple to do. And so let's write that up here. We've got, oops, that's really bad looking. We found partial z, partial x, and this is negative x over z. And so actually, if you go through and you do the same thing, except you change what you're finding. So instead of finding this with respect to x, instead if you find it with respect to y, so partial z, partial y, what you'll find is that you'll have to treat x as a constant, and then you'll get the result. If you do the same exact steps as I've done, no more complicated, it shouldn't be, you'll find that partial z, partial y will be negative y over z. And you'll actually originally get negative 2y over 2z. And so they're basically the same processes, you're just treating two different things as constants. Okay, so that's good and all. Let's try to find something a bit more spicy. So let's try to look at something that we haven't really looked at all in single variable calculus or multivariable calculus so far, which is how is x depending on y? You probably haven't really seen this too much. Maybe if you did some separate differential equations in Calc 2, you might have seen dx dy equals like x squared or something, y, for separate differential equations, but really you haven't seen how is x depending on y a whole bunch. And so we can actually take a look at that with multivariable calculus and partial differentiation, or implicit differentiation. So we'll do the same sort of process. We'll use the partial operator with respect to y of this entire function, which is x squared plus y squared plus z squared equals 1. When we take it with respect to x, we'll see that, when we take it with respect to x, we'll see that's what we're trying to find. So, okay, let me just point this out again. We're keeping z constant this time because we don't want to see how z is changing. In fact, we want it to stay constant so we can see how y is changing or how x is changing with respect to y. And so what we can do from there is take this derivative and we'll multiply by the derivative of x, which is really partial x, partial y. This is just going to be 2y. The derivative of z with respect to y. In this scenario, we're keeping z constant, so that'll be 0, and then another constant, 0. So then we're going to get, if you solve out that algebra, partial x, partial y will give you negative 2y over 2x, which gives you negative y over x. And so that's pretty cool to know.